So now that we've come up with a way to describe the motion of a rotating object, we want to describe how that rotational motion actually starts. So to do that, we need to come up with rotational equivalents for force and mass. So first, let's look at torque. Torque is basically the equivalent of force for rotational motion, and net torque causes an angular acceleration, similar to how a net force causes acceleration. So first we need to define some terminology. So here we have some lever that's rotating around an axis of rotation, and a force is applied at this point P on the lever. And so the line of action of any force is the line along which this force lies. And then the lever arm, which is represented by this L, is the perpendicular distance from the axis of rotation to the line of action of this applied force. So it's always perpendicular to the line of action of the force. So if we have this force F applied at point P on this lever, and point P is this distance away from the axis of rotation, we can calculate the torque, which is represented by this letter tau, by doing times the magnitude of F times sine of theta, where theta is the angle between this line and the force. And we can also say that torque is equal to F times L, where L is the lever arm. And these are the same because, as you can see here, times sine of theta is the same thing as the lever arm. And so torque is, this just calculates the magnitude of the torque, but torque is a vector, so it also has a direction. So if we want to determine the direction of the torque vector, we use something called the right-hand rule. So the torque vector either points directly into the paper or directly out of the paper. It's in the third dimension because it's always perpendicular to both of these and F vectors. So to determine the direction of the torque vector, you basically make a fist with your right hand and then point your thumb straight up. And then if you position your hand so that your fingers curl in the direction that the torque makes the object rotate, then your thumb will point in the direction of the vector. It should either point directly at you or directly into the page. And the same rule can be used to find the direction of the angular velocity vector. And so the unit of torque is Newton meters. And Newton meters is also joules, but they are very different quantities. So we say torque is Newton meters, while energy is joules. So the equivalent of mass for a rotating object is the moment of inertia. So this just measures how hard it is to get this object to rotate. And so the moment of inertia of one point, if this point is a distance from the axis of rotation, is m squared. So if we have a rotating object that has multiple point-like objects in its system, then the total moment of inertia of the whole object is the sum of the moment of inertias of each of these points. So it'll just be the sum of the m squareds for each point. So here we have an example rotating object, and it can be represented as 2 points because there are 2 blocks, and we just ignore the mass of whatever is holding them together. So each of these blocks is a distance from the axis of rotation, and it has a mass m. So the overall moment of inertia of this object is the sum of the moment of inertias of these two blocks. So it's just 2m squared. Now, we can use this if we can represent an object as a bunch of points. But if we have a continuous shape, such as a solid, like a ball, then they are basically infinite points. So it's more complicated to find the moment of inertia. So if you need to use the moment of inertia of these continuous shapes, you'll most likely have some kind of formula sheet for the shape, or it'll tell you. But the most common objects that you'll be using are a solid cylinder, for example, any pulley, and a solid sphere, for example, the Earth. So the moment of inertia of a solid cylinder is 1/2 m squared, where capital M is just the mass of the whole cylinder, and capital is the radius of the whole cylinder. And so the moment of inertia of a solid sphere is 2/5 m squared. So now that we have a rotational equivalent for force and mass, we can use the Newton's second law in its rotational form, which is just the net torque is equal to the moment of inertia times the angular acceleration. And here you have to use radians for the angular acceleration, not revolutions. So let's look at an example. So we have a 60-kilogram rollerblader, and he's holding a 4-meter long rope, which is tied around a metal pole. And then you push the rollerblader with a 40 Newton force, causing them to move in a circle around the pole. So we want to find his angular acceleration. So here you can see a force diagram for the rollerblader. We have your force of you pushing him, and then the tension force provided by the rope. So notice how the tension in the rope does not actually cause any torque, because it's the line of action of this tension force passes through the axis of rotation. So the lever the distance between the axis of rotation and the line of action is 0. So the only thing that causes torque on this rollerblader is the force of you pushing him. And this torque is the force, 40 newtons, times the lever 4 meters. So the torque that you provide is 160 Newton meters. So next we need to find the moment of inertia of this system. So this whole rotating object can be represented as just one point, the rollerblader. So his moment of inertia is just m squared. And so he's 4 meters away from the axis of rotation. So his moment of inertia is 960. And so the units of moment of inertia are just kilograms times meters squared. So then his angular acceleration is the net torque divided by the moment of inertia, which is 0.17 radians per second squared.